Welcome back to Ansys' video series on fluid simulation of a supersonic rocket. In the last video, we learned how to import a clean CAD file of the rocket body solid. In this next video, part 2 of the series, we'll explore how to generate the fluid domain for simulation, use name selections to streamline the Fluent workflow, and prep the final geometry for meshing. Now that the geometry has been cleaned and merged into a solid rocket body, along with inserting a void space at the tail to represent the nozzle, we can create a fluid volume surrounding the solid. To do so, we'll use the Prepare tab and the Enclosure tool, which will enclose the solid with a shape. The default is a cylinder, but you can also use a box, a sphere, or custom shapes. And the dimensions of the domain are adjusted using rules of thumb for supersonic external aerodynamics. The upstream, downstream, and radial dimensions used are based on the characteristic length and diameter of the current rocket being simulated. These dimensions will vary based on rocket geometry, but should be sufficient for the initial simulation. It can also be seen that the fluid enclosure created also creates a void space where the solid body is. To reduce the computational cost of this simulation, we'll utilize the symmetry of the geometry and split the fluid domain into a quarter wedge shape. To do this, we'll define planes and move those planes in 45-degree rotations to create the quarter wedge clipping planes. Then once the planes are defined, the Split Body tool can be used to select the geometry you want to split, select the planes used to split the geometry, and then you can see there the fluid domain is split into 4 quadrants. The enclosure object is now 4 separate objects, and the unwanted objects can be deleted. The same operation can be done for the solid rocket body. However, instead of deleting the objects through the object tree, we can use the delete part option of the Split Body tool. Now we're left with only the quarter wedge of the rocket and the fluid domain. Next, we'll rename the objects and assign named selections to each surface of the fluid domain. This will help with Fluent simulation setup and with naming conventions for the inlet, far field, outlet, walls, and specifically, the symmetry name selections will help with assigning the symmetry boundary condition in the Fluent setup. The symmetry condition is assigned to both sides of the wedge so that it can be stitched together to represent a full 360-degree simulation upon completion. Adding the nozzle inlet to the name selections allows for the inlet boundary condition to be used in the simulation setup later on. This is important because this surface is where the nozzle discharge and the rocket exhaust will enter the fluid domain. Once all named selections are added, all components are shown and then name selections are hidden to ensure no surfaces were missed. Here, the top of the fin was missed, and it's added and merged with the fin wall name selections. Next, bodies of influence are created within regions of the domain where increased mesh resolution and grid sizing is required. This will help better control the mesh size in Fluent meshing. The sketch tool is used to draw shape around the fin to capture key flow features such as shock waves from the fin surface. When back in 3D mode, this sketch becomes a surface which can be extruded to fully enclose the fin body. When pulling this surface, ensure that no merge is selected so that a separate body is created from the extrusion. The overlapping objects must be in separate components in the object tree, and the body of influence, named BOI, for proper selection and local sizing controls in Fluent meshing. The sketch tool is used to create multiple overlapping bodies of influence for different regions of interest of the domain, including the nose cone, the body, and the exhaust. Here, the surface is pulled and rotated 90 degrees to match the wedge shape. Finally, a body of influence is created for the rocket exhaust, where mock diamonds are expected due to significant changes in pressure and density of the fluid. Now ready for simulation, the fluid domain is sent to Fluent through the watertight geometry workflow extension in the Prepare tab. The number of cores is selected in the working folder, and Fluent is started. It automatically starts in meshing mode when started from discovery. If your simulation goal is to design the rocket body through a parametric study, then instead of transferring to Fluent meshing, you can open the Save Discovery file with Workbench and set up the workflow there. The full parametric setup is discussed in future videos.